Good afternoon, KAMS. This is Mr. Navarro, and welcome to your Friday lesson. Today I'm going to take you through a review of Chapter 1 and up to Chapter 2.4. If you've missed any of our lessons or activities, please make sure that you go back and go through those video lectures and demonstrations. Today's lesson is to act as a review of all of those concepts and ideas. So make sure that you watch this with care and thoroughly before you begin your quiz and practice problems for the weekend. So let's get started. Our unit is on populations and resources. So first off, our founding question, we're studying this mystery moon jellyfish increase in the Arctic Sea. Things that we need to know as far as a conceptual knowledge of animals and populations are as follows. Definitions for an ecosystem: it's all things that are living and non-living in a particular area. So for our study of the jellyfish, we're talking about that Arctic Sea area. An ecologist is a scientist who studies ecosystems. So they'll be looking at the interactions of organisms with one another and their environments, that's the living and non-living things. A population is a group of the same type of organism living in an area. Ecologists study changes in the size of populations. So they're looking at specifically, in our case, this moon jellyfish population. They're looking at what is causing that population to bloom or to grow. But populations can change from growing to shrinking, or from shrinking to stabilizing. There's many ways it can move. Within a population, organisms are always being born and dying. That goes amongst all living organisms. So we can't just assume that a population, if we do a head count of a population once every year and it remains around 50, that nothing has ever been born or died. Living and dying occurs all the time, so that's something we have to factor in when we study these populations. In Chapter 1.3, Births and Deaths in a Population, we studied exactly that. We looked at a meerkat family, a meerkat population, over a 7-year period of time. Our warm-up question for that unit was saying that scientists have been studying this one population for a long time and noticed that its numbers stayed the same over time. We were asked to explain how that is or what caused that. The incorrect conclusion was that no meerkats were died of old age, were eaten, or anything of that factor, that they all lived for a very long time. The truth of the matter was that births were constantly happening and deaths were constantly happening. But those births and deaths will cancel each other out as far as an overall population number over time. So, how does this work? We increase a population by having more births than deaths over a specific period of time. We have similar numbers of births and deaths over time, which will stabilize a population. And if we have more deaths than births, it will decrease the population. In the model I've given you below, we started off with a population of 13 organisms. In year 1 of a 6-year period of time, 2 were born, 1 died. So that basically brought our population up to 15 with the births, back down to 14 with the death, and at the end of year 1 we had 14. If you run this model, you can do the math and figure out how that works. If you've got a balanced chart, then you should have the number of births totaling over here and the number of deaths totaling here. The difference between the two should be the difference between your starting number and your finishing number. Stability and change in a system. Now, this is the same concept as the chart, but we're going to be watching a quick video on stability and change in a system using water. So we're looking at a container that water is flowing into and out of. When we add more water in than is leaving, the population will increase. When we when we take away more water than we're adding, it will decrease. And if we're adding and taking away the same amount at the same time, that population inside the system will stay the same.
This is a system. The system is stable, meaning the level of liquid isn't going up or down. But that doesn't mean that nothing's happening in this system. This top valve allows liquid to be added to the tank, while the bottom valve allows the liquid to be removed from the tank. Right now, the amount of liquid being added is the same as the amount of liquid being removed. This makes the system stable because the level of liquid stays the same over time. If either the amount being added or the amount being removed changes, the system will no longer be stable. It will change. The level of liquid will increase or decrease. If we change the valves so that more is being added than is being removed, the level of liquid will increase. This can be done by either loosening the top valve to let more in or tightening the bottom valve to let less out. Either way, the effect is the same. More is being added than is being removed. Now let's try to get the level of liquid to decrease. To get the level of liquid to decrease, we need to change the valves so that less is being added than is being removed. We can do this by either tightening the top valve to let less in or loosening the bottom valve to let more out. Either way, the effect is the same. Less is being added than is being removed. The liquid will decrease. So a system can be stable even if something is being added and removed from the system, as long as the amount being added equals the amount being removed. But if the amount being added or removed changes, the system will change. If more is added than removed, the amount will increase. If less is added than removed, the amount will decrease.
Moving on, Chapter 1.4, Births and Deaths in the Jelly Population. As we just witnessed on the demonstration on the graph, on our table, as well as the video, a system can be stable even as things are being added to and removed from it. If the amounts being added and being removed are not equal, then the system will change. So, if the number of births and deaths in a given time are equal, the population size will be stable, meaning it stays the same. If there are more births than deaths in a given time, the size of the population will increase. If there are fewer births than deaths, the size of the population will decrease. All right, Chapter 1 is a wrap. Moving on to Chapter 2. This is the topics that we've covered this week so far. So if you're just joining us today for our first time, this will be new information for you. For those of you who have tuned in and done your lessons this week, this should also be a nice review. So, new chapter question. So first off, our unit question: why did populations change in size in an ecosystem? Our Chapter 2 question: what could have caused the births? I apologize. Wait for 1 second. What could have caused the births to increase or the deaths to decrease in the moon jelly population? So our vocabulary still is staying the same. We are adding a few more words as we move on. But the key things we must know are our ecosystem. What is energy? Energy is the ability to make things move or change. And that's pretty much it for right now. So Chapter 2.1, Reproduction and Energy. Organisms need energy to live and reproduce. The more energy available, the more reproduction is possible. All that basically means is that in order for things to live, they must have energy to keep them alive. Whether they're moving around or sleeping, all things are consuming energy at all times as long as they are living. Organisms consume energy storage molecules. This is a new vocabulary term for you. Those are molecules that hold energy that can be released when organisms digest them in their bodies. Organism populations that eat other organisms are called consumer populations. So if we look at this model at the top, this owl, he is a carnivore, and he will eat other smaller animals to consume their energy storage molecules. The mouse will eat the grasshopper, will also eat the grass. The grasshopper will eat the grass. The grass will consume nutrients from the soil and solar energy from the sun and water as well. So this would be the chain. So consumer population, consumer population, consumer population, and then here would be resource, resource, resource as far as the owl goes. Organism populations that are eaten by consumer populations are called resource populations. So once again, going down this way would be the consumer way, going up this way would be the resource way. When we look at energy storage molecules, a couple of very common types, carbohydrates and fats. So we have starches, glucoses, and lipids. On Tuesday's lesson, we actually did a lab where we explored these energy storage molecules. That definition, again, it's a molecule that organisms can use to release energy needed to survive. Organisms must do this in order to reproduce. And on Tuesday, we set up an experiment, what you see here over on your right-hand side of the screen, where we had dried yeast, we had sugar, we had warm water, and 3 separate containers. We basically did the following things. We wanted to set up this experiment to show yeast, which is a living organism, how it can increase its energy, its activity, and its reproduction by consuming energy storage molecules. So the yeast experiment, what we did, I'll actually show you on this following video, but you need to understand that yeast are living things, and this bag over here is a bag of dried yeast. When they're activated, they will consume glucose, which is a sugar, and use them as energy storage molecules. The byproduct of releasing that energy from those storage molecules when yeast consumes glucose are carbon dioxide gas and ethanol alcohol. I've given you their chemical formulas as well. So let's go ahead and watch that experiment. Here's our yeast experiment setup. I have 3 glasses, each filled with yeast, 3 stirring spoons. I have 150 milliliters of warm water and a bag of cane sugar. In glass A, I will be putting no sugar. In glass B, I will be putting a pinch of sugar, which is literally the amount that you can fit between your fingers. And then in glass C, I will be putting 1 teaspoon. Once those have been added, I will add 50 milliliters of water to each glass, stir, and we'll observe the results. As you can see, I've added just a pinch of sugar. I've added a tablespoon of sugar and no sugar. Here comes our water. As you can see, I have 150 milliliters. I'm going to be putting 50 in each glass. I know the experiment says 40, but this is easier to measure. Now we will stir each of the substances. So as you can see, we've now thoroughly mixed all of the substances, and we'll check back in about 5 to 10 minutes to see how they're doing. Okay, so about 5 minutes have passed by. We're looking at glass A. You can see there's a little bit of sediment on the bottom with some white foam on the top, or lighter colored foam at the top. Not too much change other than that. When we slide over and compare to B, you can obviously see a lot more of that layer of foam, the sediment on the bottom. Remember, we had equal parts yeast, equal parts water. This one had a pinch of sugar. This one had no sugar added. So A to B, and now here's comparison B to C. So when we slide back, we can see the similar type of reaction. We can see a thicker layer of foam on the top, more sediment on the bottom, and then a pan out so you can see A, B, and C. Remember, all three equal parts yeast, all three equal parts water. A had no sugar, B had a pinch, and C had a tablespoon. And for an update, now we've had about 10 to 15 minutes that have passed by, and you can see the results again in glass A, glass B, glass C. So once again, those byproducts we talked about that are released when yeast are actually consuming glucose, on the opposite end of the chemical reaction scale, besides energy that's being released, you actually have carbon dioxide and ethanol alcohol. You can see the carbon dioxide results here in that foam that's being created at the top of each glass. The excess amount of carbon dioxide up here, this one had the most yeast in it, and had the most sugar fed to it. So obviously the yeast was able to consume more sugar. There's more available. It's able to consume more and produce more of the byproducts. Chapter 2.3, we had births changing in a population. So we wanted to take a look at how do populations increase birth rates. Well, following that same concept from our yeast experiment, we can understand that organisms need to release energy from energy storage molecules in order to reproduce, that organisms in consumer populations get storage energy molecules from eating organisms in resource populations, and the more access to energy storage molecules to a population, the more the organisms in that population can reproduce. To demonstrate this, we did a simulation on Amplify. These were the instructions, so you can take a moment, pause if you need to, pause the video if you need to, and understand what was being demonstrated. The key here was that we are going to increase the green leaf population to drastically flood the wee bed population with more energy storage molecules. Again, the more access to energy storage molecules, the more availability of energy for the wee bugs to reproduce. The following video demonstrates that. So you'll notice I let the simulation run for 20 seconds. We went to the analyze function, and we observed an uninterrupted normal status of wee bugs being born. There were 21 being born. I reset the model. I increased the resource population for those wee bugs, so basically allowing them to have more access to their energy storage molecules. Then we reset the simulation. Sorry, we didn't reset. We ran the simulation for 20 seconds, so you're actually able to see the time elapse. And then we went to the analyze function and noticed a significant increase in the births of wee bugs. So, in the last chapter, chapter 2.4, we wanted to see what would also happen if deaths were changing in a population. So we've obviously learned how births can be changed inside of a population, but we are not sure that the births of the jelly population actually increased. So a decrease in deaths could also have led to an increase in the size of a population. So it's kind of an inverse relationship. Maybe there's a higher population of jellyfish, not because more were born, but because less died. Think about that water system video, and that'll kind of give you an idea. So yesterday's sim, the one that we just watched, focused on the wee bug's birth rate. We observed that stable population for 20 time units. We then increased the energy storage molecule supply drastically, and we saw that increased birth rate because with more energy available, more reproduction was possible. In today's sim, we focused on the factors that would increase the death rate in a population. So here comes that simulation. So here, I ran the simulation for 20 units, observed the death rate of the wee bugs, which is about 24 dying and 25 being born. So you can kind of see how that is a positive gain for the wee bug population. It's stable, if not increasing by 1 unit. Reset the simulation. And increase the consumer population of the furbles. So these are those little creatures that eat the wee bugs. I maxed it out and then locked that population in. I then ran for 20 more time units. And what we're going to see is how does this impact the death rate of the wee bugs. Remember, it was at about 25 deaths in the last 20-second run. Let's see what happens when there's more predation happening. Well, right there you can see that 34 died and only 12 were being born. So now we're seeing a negative impact on the population of the wee bugs. One other factor that can affect the death rate of a population is if its resource population is diminished. So in this exercise, we are going to, instead of increase the green leaf population, which is what wee bugs eat, we're going to almost erase it. We're going to bring it all the way down to a very small margin. Then we will lock that population in. We'll leave the furbles alone. And then we'll run it for 20 more time units. So now the wee bugs only have a limited number, very scarce amount of food, and so we're going to see how that impacts their death rate. So when we zoom in and check, you'll notice that 28 died and only 1 was born. So while its death rate did increase slightly from 24, 25 to 28, you'll notice that it's not replenishing its own population. So what happened from our simulation? Well, we saw that an increased number of a wee bug's consumer population would lead to more wee bug deaths. Poor little wee bug. And a decreased number of the wee bug's resource population would also lead to the wee bug's death. For today's assignment, you will need to take your quiz covering Chapter 1 and up to Chapter 2.4 on a Google form. And then you'll need to complete your practice problems for homework. If you have any questions, feel free to reach out to me on Google Classroom. Other than that, have a great weekend, and we'll see you Monday.